Okay, let's start. I hope you can hear me.
Yes, yes.
Okay, good. So what we did last time was this ramification filtration, the lower numbering, the upper numbering. And maybe we had not determined the upper numbering for this extension when what is this? For this extension L of k, where k is QP itself and L is obtained from k by adjoining a primitive p to the mth root of unity. So m, of course, is some integer greater than 1. Okay? So for this, of course, we had determined the Galois group. We had seen that this can be identified with z mod p to the mz star. And we had determined g lower u, g sub u, for every integer u. But of course, determining g lower u for integers u is the same as doing it for all real numbers u, because in general, g of u is equal to g of, you take the integral part of, or what is sometimes called the ceiling of, this is called the ceiling of u, right? So here u is any real number. This ceiling is, of course, an integer. And for integers, we have determined what this g sub u is. Now I would like to determine g sub v for v, any real number which is greater than -1. So this is what we would like to do next. So for that, let's abbreviate by AM. Yeah, let's abbreviate by AM this multiplicative group of z modulo p to the m star. Of course, as I said, we have identified this with the group G, that's the isomorphism. It takes a C here in this group to the automorphism in G, which takes zeta p to the m, this primitive p to the mth root of unity, to its cth power. This C is taken to the automorphism, which takes the primitive p to the mth root of unity to its cth power. Okay, so that's an isomorphism. It's the inverse of what is called the cyclotomic character. And let me define A sub m upper I to be the kernel of the map from AM to AI. So concretely, of course, it's a map from Z mod P to the MZ to Z mod P to the I, where I is between 0 and M. Of course, when I is 0, this group is trivial. So, so G0, sorry, what is it? Wait a minute. So AM0 is going to be just the whole of AM. Right? This definition of AMI gives you AM0 equals the whole of AM. But for I greater than 1, that was for I equal to 0. But for I greater than 1, the number of elements in AMI is p to the m minus I, because the number of elements in AM is it's p minus 1 times p to the m minus 1 number of elements in AI, the order of AI is p minus 1 times p to the I minus 1. And this map from AM to AI is surjective. So the kernel of this map has order p minus 1 times p to the m divided by p minus 1 times p to the I, which is p to the m minus I, right? So that's what I said here. Now the proposition says that in the upper numbering, of course, G0 is equal to G minus 1 equal to G. G minus 1 is always equal to G. Why is G0 equal to G minus 1 in this case? That's because the extension, what is it called? It's called L, or yeah, it's called L. Because the extension L over K, K is QP, L is QP zeta P to the M, is totally ramified. So G0 is equal to the whole of G. The inertia group is equal to the whole group because it's totally ramified. Okay, so that takes care of G0. I'm just recalling what we had done last time, and this proposition was done last time. It says that if U is in between 1 and p minus 1, U is an integer. It's enough to do it for integers, as I said. So if U is between 1 and p minus 1, then G sub U is AM to the AM1. So here the exponent of P is 1, and that exponent is here. Similarly, when U is between P and P squared minus 1, this squared is here, this exponent. In this case, when U is between P and P squared minus 1, GU is equal to AM2. And so on. It continues for every I. You can imagine what it's going to be when, okay, let me just write it down if you want. It's P to the I minus 1, P to the I minus 1. Then G sub U is going to be, of course, AMI. So this is for I in, so 1, 2, what is it? M is allowed or not allowed? I think M is allowed, yes. M is allowed. Yeah. But this U cannot be P to the M, because here P to the M is excluded when I is equal to M. Okay, but when U is greater than P to the M, then the group GU is trivial. So that's what we had done last time. That is the ramification filtration for this extension in the lower numbering. Okay. Now here seems to be a definition. So let's forget about this particular extension. Let's take an arbitrary P field K, an arbitrary finite Galois extension L of K, and let G be the Galois group. In this situation, we say that some real number U is a lower ramification jump or break, sometimes also called a break. If, I mean, for this group G, if for every epsilon, strictly positive epsilon, I mean, however small you might take it to be, G of U plus epsilon, which is a subgroup of GU, should not be equal to GU. It should be a proper subgroup. That's when you say that this U is a lower ramification break. Or jump. So obviously, if u is a lower ramification jump, then u is an integer, because for a real number which is not an integer, cannot be a lower ramification break, because gu for u real is equal to g this, and so if your u is between m and m plus u is here, then in fact for sufficiently small epsilon, u plus epsilon, for sufficiently small epsilon, the ceiling of u plus epsilon is going to be equal to the ceiling of u, right? In both cases, the ceiling is m plus 1. So if u is not an integer, it is strictly between two integers, then for sufficiently small epsilon, the ceiling of u plus epsilon is of course equal to the ceiling of u. And therefore, this you can't have inequality here, you'll have equality. Fine. So if a lower ramification jump occurs at u, then u has to be an integer. Now, there's a similar definition for upper ramification jumps. So we say that v is an upper ramification jump for this group G. G has a filtration in the lower numbering, and essentially the same filtration is renumbered differently, and that's called the upper numbering, right? So in the upper numbering, V is called a ramification break in the upper numbering, or an upper ramification jump, if for sufficiently small, for every epsilon, strictly positive epsilon, no matter how small you take it to be, g of v plus epsilon is different from, is a proper subgroup of g upper v. So as in the case of lower ramification jumps, it does not follow that if v is an upper ramification jump, then v is an integer. Does not follow. So there are upper ramification jumps which are not integers. Actually, I mean, if u is a lower ramification jump, this implies that, what is it? Phi L over k of u is an upper ramification jump. And similarly, v is an upper ramification jump, implies that psi L over k of v is a lower ramification jump. So they determine each other. Yeah? There are these functions phi and psi, which determine the lower filtration in terms of the upper one, and or rather the lower numbering in terms of the upper numbering, and the upper numbering in terms of the lower numbering. So this was for a general Galois extension, right? This is a general definition. When K is a P field, the group G has filtration. The filtration has two numberings, so to speak, the lower and the upper. And then there's this notion of a lower ramification jump and an upper ramification jump. So for example, in this terms of this definition, if we come back to this situation, right? Come back to our k equal to qp and L equal to qp zeta p to the m, where zeta p to the m is a primitive p to the mth root of unity, right? M is some strictly positive integer. G is the Galois group. We know that it's isomorphic to AM, which is defined to be Z mod p to the m Z star, and the proposition that we had proved last time amounts to saying that the lower ramification jumps of this G occur at p to the I minus 1 for all I between 0 and m. That's exactly what this is saying. Where is it? Here it is. So here it's p minus 1, here it's p squared minus 1, here it's p to the I minus 1, etc. all the way up to I going from what happens for I equal to 0, p to the 0 minus 1 at that's 0. Does a jump occur at 0? Yes, it does. Oh, well. It doesn't if p is equal to 2. So one should say I goes from 1 to m if p is equal to 2. Otherwise, it goes from 0 to m. These are the lower ramification jumps of the group G, when G is, of course, this special extension of QP obtained by joining a primitive p to the mth root of 1. It's called the cyclotomic extension, right? Okay. So here is the explanation, right? That these are G, well, what I've explained is written here again. And the exception p equal to 2, I equal to 0, that doesn't, it's not a jump, because in this case, G0 is equal to G1, because the index here is, the quotient here is Fp star, and Fp star is trivial when p is equal to 2. That is the reason why for p equal to 2, there is no jump at I equal to 0. Yeah, when p is equal to 2. Okay, right. Fine. Okay. So now let's compute the upper ramification jumps for this extension. That's not a difficult problem. It's just a matter of computation. We know that the upper ramification jumps are going to be just phi L over k of p to the I minus 1, where I is in, what is it? 0 to m. If p is different from 2, and I is in 1 to m if p is equal to 2. So we just have to compute these things. And we can, of course, compute it because our function phi is given explicitly. So let's look at, so here is the computation. It says the upper ramification jumps for this, first of all, are all integers. So in general, it's not guaranteed that the upper ramification jumps are integers. Okay. But in this case, they are integers. And what it says, in fact, is that that GV, G upper V is AM upper V for every integer V in 0 to between 0 and m. And if this V is greater than m, then this G upper V is trivial. Why am I specifying it only for integers V? Because the breaks occur only for integers. Therefore, this filtration is uniquely determined if I specify what the groups GV for V in Z are. If the breaks had occurred somewhere else, then this information would not be sufficient to determine the filtration. Okay, so why do the breaks occur at integers? We don't know. We just have to compute. We know that the upper ramification jumps occur at phi of these things. These are the lower ramification jumps, as we have just calculated, where I is in 0 to m if p is different from 2, and 1 to m if p is equal to 2. So it's enough to prove that phi of p to the I minus 1 is equal to I. And well, I have not proved it. I'm just saying that it follows from the definition. You just have to plug in whatever the definition of phi was, and as an integral, right? And that's it. So, yeah. So the upper ramification jumps occur at the integers I between 0 and m if p is different from 2, and at the integers between 1 and m if p is equal to 2. And in fact, I mean, something p equal to 2 is special, because when I adjoin to Q2 a primitive second root of unity, right, square root of 1, I mean, that is just an extension of degree 1. Whereas if p is different from 2, then I get QP, and when I adjoin, what is it, pth root of 1, then I get an extension of degree p minus 1, which is not trivial. Huh? So this extension is not trivial, whereas for p equal to 2, it's trivial. Okay. Now, let's consider the special case. Let's come back to, first of all, a general p field K and a finite Galois extension L of K, and assume that it is actually a cyclic extension of prime degree. Okay, these are, of course, the simplest kind of Galois extensions one can imagine, because cyclic groups are the simplest kind of groups one can imagine. So if it is cyclic of prime degree, then there has to be a unique ramification break, lower ramification break or upper ramification break, right? And in fact, the upper ramification break is going to be the same as the lower ramification break. Why is there a unique ramification break? Because, I mean, you have CL, then the only subgroup can be either, I mean, the only subgroup is either trivial or the whole of CL, because it's cyclic of prime degree. It has no subgroups, no non-trivial proper subgroups. So, yeah, it's a cyclic group and has no subgroups other than the trivial group and the whole group. Okay, so it has a, if I have a cyclic extension of prime degree, this prime is, of course, may or may not be equal to the prime P. This prime L, the degree of the extension, may be different from the prime P, which is the residual characteristic of the field, local field K, or it might even be equal to the residual characteristic. We'll see that the two cases are very different, because in one case, it's a tamely ramified extension, and in the other case, it's a wildly ramified extension. We'll come to it. Let's see. So let's go about it slowly. So the question is, since a cyclic extension of prime degree has a unique ramification break, we might ask, where does this break occur? Can it occur at 2, 3, whatever, 1, 2? I mean, can you say something about where the break occurs? And let me call it T, give it a name, and then the question becomes, what is T? So T, by definition, C lower T is equal to the whole of, it's already called, it's called CL. So that's it's a conflict of notation. But the group is called G, so there's no, so now, okay, let me just call it C. Let's just call it C, and it's a cyclic group of order L. And the group, the Galois group is, it's isomorphic to C, which is a cyclic group of order L. But the Galois group, I'm going to continue to call it G. So G sub T is equal to the whole of G, whereas G T plus epsilon is trivial for any epsilon which is strictly positive. Okay. So I'm saying if this L is different from P, then L over K is either unramified, right? In which case, of course, this G sub U is equal to G if U is minus 1, and it's equal to, it's the trivial group. G sub U is the trivial subgroup if U is strictly greater than minus 1. Because G, whatever, we have seen this, right? This, I don't need to explain this again, right? That's what it means for it to be unramified. So the break occurs at minus 1, T is minus 1. Or it could be totally but tamely ramified, right? Totally ramified because the degree is prime. Prime degree. So it's ramified means the ramification index divides the degree, and the only number which divides a prime number is the prime number itself. So the ramification index has to be equal to this L, and therefore this extension is totally ramified. But it's tamely ramified because this L is different from P. That's our assumption. We are working in that assumption. So it's totally but tamely ramified. And in this case, what happens is that this G sub U is equal to the whole of G if U goes from minus 1 to 0, including U equal to 0. But if U is ever so slightly bigger than 0, then G sub U is trivial. This means that the unique ramification break occurs at 0. T is equal to 0. So the case L different from P is, this was easy. There are only two possibilities. The unique ramification break occurs at minus 1 or 0. This is in the unramified case. And this is in case the extension L over K is ramified. Okay. The question arises as to what happens when L is equal to P. There's a most interesting case, of course. Often in number theory, you have two prime numbers which are floating around. If they are different, then things are relatively easy. If they are the same, then things are very, very complicated. For example, you just look at QP, extensions of QP of degree L different from P. If you want to classify them, they are going to be easy. But extensions of QP of degree equal to P, they are somewhat hard. Okay. But right now we are looking at cyclic extensions of QP, not just QP, but any P field any p field K, we are looking at cyclic extensions of degree equal to P. So what happens for this case? This is, as I said, it's not an easy question. I mean, okay, it's not all that hard either, but we will come back to this later. Okay. So let's slightly change gears and look at extensions. So the simplest groups, of course, are cyclic of prime order, right? Next simple, I mean, these things are also simple in the technical sense of not having any non-trivial subgroups. Huh? But the next simple, sorry. Is there there is some extraneous noise coming in. I'm going to mute everybody. Well, hello.
Yes,
Okay.
sir. Yes, sir.
Yeah, fine. So the next simple groups in this sense are, of course, these are abelian groups of exponent P. Abelian groups of prime exponent. So that's a fancy way of saying these are groups of the form Z mod Lz to the power R, where L is a prime, right? And R, of course, is some integer. So these are actually just FL spaces. And we've seen that cyclic extensions of a P field of degree, prime degree L, are easy. And if we wanted to classify, so so if we want to, what is it? Let's take K to be a P field, G to be isomorphic to Z mod Lz R, right? And if we take L to be different from P, then all G extensions of K, which means a Galois extension whose Galois group is isomorphic to G, these are easy to classify. Okay. So that was when L is different, because here it's everything is tamely ramified, right? And we have discussed tamely ramified extensions extensively, and we have determined when they are Galois, when they are abelian, and so on. So there's nothing really that we have left out. What we haven't discussed are abelian extensions of exponent P, where P is the same as the characteristic of the residue field. So let's look at this. Let's look at this case. K is a P field, L is a finite Galois extension. In fact, it's an abelian extension. It's an abelian extension, and the group G is killed by P, where P is the same prime as the characteristic of the residue field. Then the proposition says that an integer V, not an integer, but a real number, is an upper ramification break for this group G if and only if there is an intermediate extension between K and L. K and L, there's an intermediate extension E. We are looking at the extension L over K, right? V is a upper ramification break for the Galois group of K over L, if and only if there's an intermediate extension E, which is cyclic of degree P over K. Should be cyclic of degree P over K, and for which V is a ramification break. Basically, what this proposition says is that if you want to understand upper ramification breaks for groups which are isomorphic to Z mod PZ to the power n, then you just need to restrict yourself to the, you may restrict yourself to the case n equal to 1. That's what? Cyclic of degree P. And the general, we are looking at groups which are isomorphic to this. So some real number V is an upper ramification break for this G, which is isomorphic to Z mod P, PZ to the power n, if and only if there's an intermediate extension E, which is cyclic of degree P over K, for which V is an upper ramification. Here I've not written upper or lower, because for a cyclic extension of prime degree, upper ramification breaks, I mean, it's not a plural. There's a unique ramification break, and it's the same in the upper as well as the lower numbering. So it could be, you could write insert upper or lower here, doesn't matter. So as a corollary, the upper ramification breaks of G are integers. In this case, when G is isomorphic to this group, we have seen one more example where the upper ramification breaks are integers. That is QP adjoint a primitive P to the mth root of unity. Upper ramification jumps are integers. Now we are looking at L over K, and the only thing is that this group is isomorphic to Z mod PZ to the n, which is not the same as Z mod P to the nz, right? So here also, in these two situations, the upper ramification breaks are integers. So that's the proposition. I'm claiming that the upper ramification breaks for G are precisely the ones which occur for some cyclic intermediate extension. Okay, let's prove this. So for that, I introduced this notation GV plus for every V which is real V which is greater than -1, I introduced the notation GV plus is the union of all GV plus epsilon, where epsilon is strictly positive. Okay, fine. And in this notation, V is an upper ramification break or jump, if and only if this GV plus is different from GV. Of course, we have GV plus is not +1, just plus. This GV plus is a subgroup of GV, right? In general, but it could be equal. If it's equal, V is not an upper ramification break. It's a ramification break if and only if GV plus is different from GV. Okay, so let's prove the proposition. There are two implications. I mean, we have to prove an equivalence. So let's first prove this easy part, easy implication, which says that if V is the ramification break for a cyclic sub-extension of degree P, I mean, okay, for a cyclic sub-extension, necessarily of degree P, then it is an upper ramification break for the whole of G. So let's take some intermediate extension which is cyclic over K of degree P. Let's call C the Galois group. And V is an upper ramification break for C, means that C upper V is equal to C, but C upper V plus is the trivial group. That is the hypothesis, right? But what does Erdogan's theorem tell us? Erdogan's theorem, I am going to use it in this form when I have this, and this group is, let's say, G, and this group is H, right? Then, of course, there's this map from G. Map meaning H is a quotient of G, and H sub V is actually the image of G sub V. It's not sub, excuse me. H upper V is the image of G upper V under this quotient map. That's Erdogan's theorem, right? Yeah. So this image, here the quotient is called C, not H. So by Erdogan's theorem, I'll get C upper V is G upper V bar, and C upper V plus is G upper V plus bar, where the bar or the overline indicates the image under this quotient map. This is a quotient map, right? Corresponding to what? Here the extensions are called L, E, and K. The group is C, the group here is G. So there's this quotient map from G to C. So C is a quotient of G. And by hypothesis, this is different from this. This, I mean, these two are not equal. So these two, of course, they have different images. So these two are not equal. The images are not equal. So the groups themselves are not equal. For if you had equality here, you will have equality here, and therefore equality here. But you don't have equality here by hypothesis, right? So G has an upper ramification break at V because this happens. That is the proof. That's the easy direction. And here is the slightly more difficult direction, but it's not all that difficult, as you will see. So suppose that a ramification break occurs at V, which means that G upper V plus is a proper subgroup of G upper V. Now G is an FP space. G is isomorphic to Z mod PZ to the power n. So there's now one of the properties of vector spaces is that if you have if you have vector space EV And if you have if you have two subspaces, let's call them what motion? W1 and W2, these are subspaces. And this is contained in, V1 is contained in the, W1 is contained in W2, but it's not equal to W2. If this happens, then there is a hyperplane. Hyperplane means codimension 1. Hyperplane means codimension 1. Then there is a hyperplane such that which contains W1 but does not contain W2. Okay, so here are two subspaces of my vector space G. I mean, G is the vector space over FP, right? So there is a hyperspace, hyperplane H, which just means a subgroup of index P, which just means a subgroup of index P, which contains the smaller subgroup but does not contain the bigger subgroup because they are not equal, right? Now you take the fixed field of L of this H. That's a cyclic extension of degree P over K because the index of H in G, that index is equal to P. So the degree of LH over K is going to be equal to P, right? So it's a cyclic extension of degree P. And if I put C equal to the Galois group, which is G mod H, right? Then again, by Erdogan's theorem, what is CV going to be? CV is the image of GV, and that is C because GV is not contained in H. You're going modulo H. This is the image in G modulo H, and GV is not contained in H. So the image of GV is not trivial. But if it's not trivial, then it has to be, and it's a subgroup of C, then it has to be equal to C. Whereas, what is CV plus? By Erdogan's theorem, here and here, it was Erdogan, right? CV plus is the image of GV plus, image of GV plus. But GV plus is contained in H, so the image is trivial. Now, I've got this V such that CV is the whole of C, whereas CV plus is trivial. So V is a ramification break for C. And in particular, V is an integer because for cyclic extensions, obviously the lower ramification break occurs at an integer and the upper ramification break occurs at the same integer. Okay, so what have we proved? We have proved that if we have an extension which is abelian of exponent P, if it's an abelian extension, abelian of exponent P, then a real number is a upper ramification break if and only if there is an intermediate extension which is cyclic over our field K of degree P, and for which this V is a ramification break. I think I'm spending too much time on this today. I'm going more slowly than usual. But maybe, it's if something remains, then that's the aim. So now let's recall what the exponent of the different, I mean, we had actually denoted by SL over K at various points. So if we have a Galois extension, finite Galois extension, and the group is cyclic of order P, and if the unique ramification break of this C occurs at T, then the exponent of the different, we had computed it in terms of the ramification filtration, and if the break occurs at T, then the exponent is equal to 1 plus T times P minus 1. Because, okay, I mean, I think I'd called it SL over K, you know. This D had been called SL over K earlier. That's equal to, what we had proved was that it's equal to I greater than 0, GI minus 1, right? And GI is the order of G sub I. Here, the group G is called C, so, right. So the order of the group, the GI, I mean, if it's either P or 1. So that's why you get this here. All these GIs are either equal to the whole group C, in which case the order is P, or these GIs are trivial, in which case they don't contribute because GI minus 1 is 0, and so there's no contribution. Okay, there's no contribution to the sum. Fine. So the next problem we are going to look at is that if we yes, so it's a kind of exercise really. It says that if I take a P field K and I take a finite Galois extension which is totally ramified, and the Galois group is abelian of exponent P, which is the same as saying that it's an FP space. And if I know the upper ramification breaks, if the upper ramification breaks occur at the integers T1, T2, Tn, and the index of GTI plus in GTI for I from going from 1 to n, that's where the breaks occur, right, is P to the Fi, then one has to compute the lower ramification indices in terms of these TIs and FIs. Compute the lower ramification indices in terms of TI, FI. Okay. So what is given to us is displayed in this diagram. We have the group G, and then it's equal to G upper T1, where T1 is some positive integer, strictly positive integer. This G upper T1 is of codimension F1 in G upper T2, which is of codimension F2 in, so codimension, what does codimension for a group mean? As FP spaces is what is meant. And so on, all the way up to G T to the N, which is of codimension Fn in G T to the N plus, and I mean, it's not this which is of codimension something in this, is the other way around, right? The subgroup has a certain codimension in the ambient group. So, and this GTN plus is trivial. That's the last ramification break. Okay, so then the proposition says the lower ramification breaks of G occur at L1, which is the same as T1, but this Li for I going from 2 to n are given by this formula. In terms of these, okay, recursively, in terms of these Ti's and the Fi's. Okay, so I mean, there's no, it's just a computation, because by definition, the lower ramification breaks, if you know the upper ones, then the lower ones are given by this function C. There are n of them, and they are C L over K of Ti, where Ti are the upper ramification breaks. And this function has this explicit definition. So, I mean, you look at this table, which captures the same information. I mean, you see, you're integrating this index, so all you need to know is what the index is. So here is what the index is. I mean, that's given to us. It's 1, p to the f, or this, right? These are the indices, and that's it. So, I mean, there's nothing really to prove here. Okay. Okay, so one question which we had left, which we had said we'll do later, is what happens when we have a p field k and a cyclic extension of degree p. This is, we had earlier called it a cyclic extension of degree L, where L was a prime, and we had treated the case L different from P earlier, and now we are doing the case L equal to P. So I'm just calling it degree P, sort of degree L, because L is equal to P. So the question is, where can the breaks of G occur? If in the case L different from P, we knew that the breaks can occur at -1 or 0, right? But when L is equal to P, what happens? So today we'll answer this question when the characteristic of K itself is equal to P, and next time we'll do it for the characteristic 0 case. Okay. So for that, I need to recall Artin-Schreier theory. So let P be a prime, let K be any field of characteristic P, and this Weierstrass P is the endomorphism x to the P minus x of the FP space K plus. It's an FP space, excuse me, because because the field K has characteristic P, and it's an endomorphism because x plus y to the power P is x to the P plus y to the P. So it's an endomorphism of the additive group. So what this Kummer theory tells you is that cyclic extensions of degree P are the same as, or not the same. They are parametrized by FP lines in this space K plus, which is the additive group of K, modulo PK plus, which is the image of the endomorphism P, right? This is an endomorphism of this vector space K plus, vector space over FP, and it has an image which I denote by this Weierstrass P K plus, and is the co-kernel. This is the co-kernel of this Weierstrass P, right? So if I have a cyclic extension E, it gives me, I can look at the kernel of the map from K plus modulo P K plus to E plus modulo P E plus, and that's going to be an FP line. And conversely, if I'm an FP line D, then I can adjoin every root of the polynomial PT minus A, Now, pt, of course, is the polynomial t to p minus t for every a in k plus, such that a bar denoting the image of a in this quotient, such that a bar belongs to this line D that I'm talking about. That is k p inverse D, right? So that's Kuma theory, and I'm just recalling what this is. Okay, so since it's 4, I'll stop for a few minutes to see if there are any questions. No questions. Okay. So this was for an arbitrary field K of characteristic P, right? Now let's come back to our P field K, but assume that it is of characteristic P. So it's really isomorphic to what is it called? The Laurent series field with coefficients in the residue field. And we are determining the structure of this K plus modulo Pk plus. And now when we are looking at a P field, this P is to be not to be confused with P sub K, which is an ideal in O sub K, whereas this P is a map from K plus to K plus. Two very different things, right? The map which takes x to the P minus x. Okay, so now I'm just recalling what the structure of this quotient is. K plus modulo Pk plus. What is it? So for every I in Z, let's denote by Pki bar to be the image of this ideal Pki in K plus bar. So what we had seen earlier is that Pk bar is 0. So of course Pki bar is 0 for I greater than 1. So here it's 1, but the others are contained inside this, and therefore the images of the others are trivial as well. When I is 0, this Pk 0 is of course the same as the ring of integers of OK. And what we had seen is that the image of the ring of integers is actually isomorphic to Fp. Not only is it cyclic of order P, it is a natural generator. And that natural generator actually comes from, you have OK, how do I say it? And OK goes to OK bar on the one hand. It also goes to K, or rather KK, and KK, there's this trace map, FP, and in fact, these two can be identified. So that's why this is right. And we had proved that for I strictly negative, Pi bar modulo Pi plus 1 bar, this quotient here, is equal to the same thing without the bars if I is prime to P. And it's trivial if I is a multiple of P, which just means that Pk Jp bar is equal to Pk Jp plus 1 bar for J strictly negative. Okay, and all this information is contained in this diagram here. PK is trivial, OK is the same as FP. I mean, OK bar can be identified with FP. And here the quotient is this, here the quotient is this. Here you have equality because this is a multiple of P. So you have equality here. And then this quotient can be identified with pk, what's it, minus p plus 1 modulo pk minus p without the bars, right? Here is what this quotient can be identified with this. And we had seen that cyclic extensions of degree p correspond to FP lines in k plus bar modulo pk plus. I've been denoting this by k plus bar. And this is, of course, what is it? Artin-Schreier theory. This is okay. That is for an arbitrary k. But now my k is a p field, and p fields have a special cyclic extension of degree p, namely the unramified one. And the question arises: which line does it correspond to? There has to be a special line in this field which corresponds to the unramified degree p cyclic extension, right? Okay, so this proposition says that the unramified degree p extension of k is obtained from k by adjoining the roots, the Artin-Schreier roots, by adjoining the roots of t to the p minus t minus a for all a in OK. Next. So where's the proof? So in fact, you just need to adjoin it for one A, because this, right? Because the image of OK, because OK bar is FP, and that's generated by one element, right? So if A has the image A bar, which generates FP, then we just need to adjoin the roots of t to the p minus t minus a. So let alpha be such a root, and then k alpha is the unramified extension. What we have to show is that k alpha is the unramified extension of k of degree p. So this diagram we had just seen, I mean, you have OK, and that has image OK bar, but modulo pk, you also have the residue field kk, and you have the trace map, right, which takes you to FP, and there is an isomorphism here, which makes this diagram commute. The unique isomorphism here. So basically, to show that k alpha is unramified, you just need to show that when I reduce A wasn't OK, and I take its image in kk, and I look at t to the p minus t minus a hat, this A, the image of this A, then it's irreducible. But that is more or less by construction, because this polynomial is irreducible over this finite field if and only if it's the trace of A generates this, is not zero. Okay, so that's kind of the standard stuff about Artin-Schreier kind of extensions, right? So we have proved that this line OK bar, it's isomorphic to FP. And this line in K plus bar corresponds to the unramified extension. So every other line corresponds to a ramified degree P cyclic extension of K. And ramified, it's of degree P, so it's wildly ramified. And we need to determine the ramification breaks. Okay, so let me introduce some notation in order to determine this ramification break. So let M be a strictly positive integer. Then this D, which is this FP line, will be contained in some pk minus m bar and not contained in the previous one, right? It's an increasing filtration or whatever. I mean, what you have is pk minus m plus bar is contained in pk minus m bar. So you can have lines here which are not contained in this subspace, right? So take such a line D. What we have seen is that M then has to be prime to P, because if M is a power of P, then you have equality here if M is divisible by P, right? But if there's a line which is contained here but not contained here, then you can't have equality, and therefore M will have to be prime to P. And then I take an element A in this pk minus m. After all, this here is the image of pk minus m, right? So I take an element whose image generates D, that line D inside pk minus m bar. So A bar should belong to this line and should generate this line. And then I take an alpha, which is a root of this t to the p minus t minus a, and L is the extension obtained by adjoining alpha to k. And then I take a uniformizer for k. That's the notation. I'm taking a line and it's in pm bar, pk minus m bar, but not pk minus m plus 1 bar. M is some integers which is strictly positive and prime to p. Alpha is a root of the polynomial t to the p minus t minus a, which has to be reducible, of course, over k. And L is the extension of k of degree p, of course, which is obtained by adjoining this alpha. Where alpha is, no, A is something whose image in k plus bar generates the line D. And I fix a uniformizer of k. So the first question we can ask is, can we write down a uniformizer for L? Okay, so here it is. So it says take x and y such that minus mx plus py is equal to 1. Why do you have such an x and y? They exist because m is not divisible by p, right? Sometimes this is, in some places it's called Bézout's theorem or something, the existence of such x and y. Anyway, so I have an alpha and I have pi k, so I can talk about alpha to the x. I mean, I choose any x and y which satisfy this equation. I take alpha to the x, pi k to the y, and I claim that this is a uniformizer for L, and OL is actually OK, obtained from OK by adjoining this element. I mean, this last bit is clear because L over K is totally ramified. So whenever I adjoin a uniformizer, I get the ring of integers. The ring of integers of L is obtained from the ring of integers of K upon adjoining any uniformizer of L. So all we need to do is to prove that this is actually a uniformizer of L. Okay, so the first claim is that the valuation over L of alpha, alpha is in L, right? Because L is equal to K alpha. So the first claim is that VL of alpha is strictly negative. Because if it had been positive, otherwise means if VL of alpha were positive, then of course this alpha to the P would be, so alpha would be an integer, alpha to the P would be an integer, the difference would be an integer, so this A would be an OK. But A is not an OK, right? And if A had been OK, A bar would be 0 in K plus bar. Whereas, but A bar is not 0 because it generates. Because A bar generates this D. A bar has order P in K plus bar. Okay, so VL alpha is strictly negative, and therefore VL of alpha to the P minus alpha, remember this alpha to the P minus alpha is equal to A because alpha is a root of T to the P minus T minus A. So of course, alpha to the P minus alpha is equal to A. So alpha to the P minus alpha is equal to A on the one hand, but its valuation has to be the valuation of alpha to the P because, you know, VL of, what is it? A plus B is equal to inf, or let me put it this way. Let me forget about this. Inf is VL of A if VL of A is strictly less than VL of B. Right? That is what's being used. So I'll get this here, and that is equal to P times VL of alpha. On the other hand, VL of A is P, that's the ramification index. P is equal to EL over K times VL of VK, sorry, of A, but VK of A is equal to M. Because this A belongs to PK minus M, and A does not belong to PK minus M plus 1 because we had chosen, because A bar belongs to PK minus M bar, but A bar does not belong to PK minus M plus 1 bar. That is because D is contained inside this PK minus M bar, but D is not contained in PK minus M plus 1 bar. Okay, so where do we get? So M is the valuation of A, and therefore, I mean, if you compare these two things, these two expressions, then you get VL of alpha is equal to minus M. That's right. So what is the VL of this? It's going to be minus M times X, the X coming from here, times P times Y, the Y coming from here, and the P is coming from, the P is equal, is there because V L of PK of pi K is equal to P, right? Is P times, what should I say? It's P times Vk of pi k. Vk of pi k is equal to 1, so this is equal to P. And this P is here because it's EL over K, right? And therefore, I mean, what we have computed is that the valuation of this thing is equal to 1, and therefore it's a uniformizer for L. Good. Now, finally, we are in a position to compute the ramification break of L over K. It occurs at M. Of course, the notation as before, L is equal to what I like to write as this, and D is contained in Pk minus M bar, but not containing Pk minus M plus 1 bar. In that case, the unique ramification break for L over K, or for Galois group of L over K, one should say, strictly speaking, occurs at this M, the M which is here, this M. So let's put G equal to the Galois group, and let sigma be its generator. Well, it so happens that in this case, the Galois group has a canonical kind of generator, which takes alpha to alpha plus 1. Once you have chosen to write L as K alpha, once you have chosen one of the roots, then the other roots are alpha, alpha plus 1, and so on. These are the conjugates of alpha. And there's an automorphism which takes alpha to alpha plus 1. We call it sigma, and it generates the group G. It generates the group G. So the ramification break will be determined by what the valuation of sigma pi L minus pi L is, where pi L is some uniformizer of L. In general, I mean, you can, well, forget about, right? So what I do is I take this uniformizer. I take pi L equal to this uniformizer, which I've already computed. So let me compute sigma pi L upon pi L. So it's sigma of pi L is this thing. I just plug it in. So sigma of pi k is of course equal to pi k. So this pi k disappears, and all I'm left with is alpha and this power x here. But remember, x is prime to p, right? Because what was the thing? Minus mx, yeah. The relation was minus mx plus py is equal to 1. So reducing it modulo p, I get this x is not 0 mod p, right? When you reduce it modulo p, this disappears, and x is therefore invertible modulo p. Minus m is an inverse. In particular, x is, well, x is prime to p. This x is prime to p, so I have sort of a binomial theorem which will tell me that 1 plus alpha inverse, is sigma alpha over alpha, because sigma alpha is alpha plus 1, right? So sigma alpha over alpha is 1 plus alpha inverse. To the power x is going to be 1 plus x times alpha inverse, modulo higher powers of modulo m plus 1 power of the uniformizer, because the valuation of alpha inverse is m. This is m, and then if I look at the next terms, they'll involve the square of alpha inverse, so it will involve 2m and so on. So I can ignore those things. And therefore, VL of sigma pi L minus pi L is m plus 1. And therefore, sigma is in gm, but not in gm plus 1. So the unique ramification break occurs at m. Ramification break or jump occurs at m. Okay. So here's the corollary. And so I have the difference of the exponent of the extension L over K. And I have the exponent of the different S L over K. I had a formula for this in the Galois case. And here, what you have is G naught equal to G1 up to Gm. These are all of order P, and Gm plus, no, lower. M plus 1, Gm plus 2, etc. They are all trivial. So the formula will give me this. This 1 plus m being the number of terms here. 0 is the first term, and then there are these m of these here. And p minus 1 is the order of this group minus 1, right? So that is the exponent of the different. And what is the proof? Yeah, here is the proof. The exponent of the different was the sum over all positive integers n of gn minus 1, where gn is the order of the group G sub n, and the order is equal to p minus 1 for n between 0 and m, and it's the order is equal to 1 otherwise. So the contribution of those ones is 0, and what I get is this. Okay. Now I have exactly 3 minutes left, and I don't think I can do justice to this Serre's mass formula in degree P, so I'll take it up next time. I think we just leave it for next time. Yeah. So one might mention a few corollaries that there are, or rather, in fact, every integer, every m, which is strictly positive and prime to p, is the ramification break for some cyclic extension of k of degree p. And in fact, easy to say how many. For how many extensions is this m, given m, the unique ramification break? And maybe I can leave this as an exercise, because next time we are going to use this. And in order to prove Serre's mass formula in degree P, and also for computing the contribution of cyclic extensions to that mass formula. So maybe this is a good place to stop. And maybe I was slower today than usual, but perhaps it's justified because the material might be unfamiliar to some of you. And I noticed that many of the people have found the course to be somewhat difficult going. So, okay, we should probably go more slowly. The pace today should have been okay. You let me know if you want me to be even slower. Let me stop here today.